Welcome back, Gen Chem to section 21.3. And today we are going to dive into the world of structure and structural differences between compounds with the same chemical formula. So this can be very important to reactivity, our bodies, etc. Compounds that have the same formula, we're going to look at C4H10, but different structures, that means their physical properties are going to be very different. And you will talk a lot about this concept in organic chemistry if you take that class in the future. But this is really just an introduction. We're not going to give you all the details, but enough to understand this concept. So isomers, basically two compounds like butane and methylpropane can have very different properties, but also have the same chemical formula. There's C4 and H10 in both of these compounds. So what isomers are compounds with molecular forms that are the same, but different arrangements, sometimes connections, sometimes just spatially different from each other. And as those go into our body or do reactions, they can have very different properties. So they're very different, but they have the same chemical formula. And we're going to be looking at structural isomers, cis-trans isomers, and stereoisomers. So let's go ahead and look at these two. We have butane down here, there's the straight chain, and then we have methylpropane. So notice if you count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yes, indeed, there are 10 hydrogens on either one of these compounds. Besides just their physical shape, notice that the boiling point are different. It's about 0 degrees Celsius for butane, and methylpropane is even less. So this is more volatile than this one over here, just because of that branched nature of this versus the straight chain. So that's our first example of an isomer. And these are structural isomers, and we're going to see that in the next slide here. So structural isomers, specifically, they have the same number and type of atoms, but connected. This is important. There's an actual new bond that was formed. Notice this single bond can swing around as much as we want. And I could actually draw this like this in the skeletal structure, or I could draw this like this. Those are the same compounds. All I did was swing this bond around from here up to here. Those are the same compound. That can just happen. These actually are happening all the time. These bonds can move around in space. This is a new isomer because I didn't just swing a bond around. I moved the bond connection from here to here. So I were to draw this in this way, this is methylpropane. So notice with the structural isomers, you actually have to make a different bond connection. So different connection, that's key for structural isomers and identifying them. Here's another version of that. This is the ball and stick of what I just drew. So these are the exact same compounds. These are just different orientations in space. Again, if this was my condensed skeletal structure, I'd be drawing it like that, versus if I spun this around, it would become this side over here. So now I'm just drawing it like this. For single bonds, you can draw them however you want. We tend to typically just draw straight chain alkanes like this over and over, but it's just as correct to draw this like this and just kind of draw however you like and just keep doing this. Maybe they do this because they can spin around these all the time. They're kind of like these kind of snakes, those like piece of spaghetti here. It's not just a static picture. So those are different orientations that these can take. Same compound, different orientation. Now, let's actually look and determine. So this one says, determine whether the following sets of molecules, so this one or this one, and this one or this one comparing, are isomers or the same compound. So to do that, you need to determine, are there different chemical bonds between these two compounds? Or is it simply just an orientation change, which means it's the same compound? So I'll give you a second to pause the video to do that. Okay, let's take a peek at these. Set A. What I need to pay attention to are the connections. On this carbon, there is a methyl group, and an H. So let's look at this carbon over here. Right here, there's a methyl group, and an H. Okay, so there's no different connections there. On the right-hand side, actually, I'm just going to leave that there. On the right-hand side, this carbon, there's a methyl group, and an H. And on this side, oh, you might think, oh, different compound. Well, let's just keep looking. Well, these all match up. There's a methyl group, and an H connected to this carbon. So there's no new bond connections because I can just spin this around. So this is the same compound. If you just twist this around in space, it's going to look like this. It's the same exact compound. Let me see if I can show this with, if I was going to draw this in the skeletal structure, this would be my first carbon right here. And I'm going to draw this upward to this carbon, and coming off this carbon is this one. Then I'm branched over here, CH3, CH3. So if I were to spin this around, it would look exactly the same, except now I have my hydrogen up here, and I have my CH3, CH3 down here. So all I'm doing is just spinning around this bond, spinning around that. That's all you're doing, same compound. So let's look at the next one and see. Same thing, I'm going to inspect. From this carbon, it's bonded to a CH3, a CH3, and a CH3. If I look over here, right away, something is different. This is now a new physical connection to an H. It was never bonded to an H. That is a new compound now. Looking at the right-hand carbon, I should have an H, and CH3 coming off of here. Now I have an H, a CH3, and a CH3. So those are brand new bond connections. So these are definitely not the same. These are equal, this one is the bottom. So these are structural isomers, different compound, same chemical formula. And you can double check that. How many carbons are here? 1, 2, 3, 4, 5, 6. So C6, and how many H's? 3, 6, 9, 12, 13, 14. And then over here, we have 1, 2, 3, 4, 5, 6, and 3, 6, 9, 12, 13, 14. Yeah, same chemical formula overall, but spatially, we have a new connection. Instead of just an H here, we moved that to this side, and we took one of those H's and put it down here. So structural isomers. Yeah, same compounds, structural isomers for this one here. So let's practice going back the other direction. So this problem says, draw condensed structural formulas. I'll probably draw them expanded at first. You don't have to start by doing condensed. It might be easier to start by drawing them like this, with all the hydrogens, stuff like that. So it says draw condensed structural formulas for 3 compounds with a molecular formula of this, and then name them. So we're focusing on C5H12, and let's see if we can come up with 3 different ways to draw that same chemical formula. So go ahead and pause the video here and give that a shot. Okay, welcome back. Let's take a look at this. So if I was going to do this problem, I would just simply start by drawing carbons together. 3, 4, 5. And yes, I could draw out all the H's here if I wanted, but for now, I just know that there's H's everywhere. And this would be C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12. So that's one way. That's the first way. That is a structure. How do we name this? This is a 5-member straight alkane chain. So that would be pentane. I'll just write that up there. How can we make new connection points now? So maybe you're trying this out and you thought, okay, I'm going to draw this out. 3, 4, and then you thought, okay, here we go, CH3. See, that's a CH3 on the end there. Those are all hydrogens. Is that a different compound or not? It's not, because it's not a different compound because this carbon is an HHCH3. This carbon is an HHCH3. All we did there was just kind of spin this downward. We spun this around. So remember, I need to actually move this carbon to a different carbon. I need to move this bond over to this carbon to make this a new compound. So let's go ahead and do that instead. I can draw these in now since I already started the process. I'm going to move this bond, not from this carbon, but I'm going to put the CH3 group over here. Think of it that way. So now I have carbon, 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 and instead of on the fourth carbon, I am going to draw this here. 1, 2, 3, 4, 5. There we go. All the way over here. Okay, now that's a new connection point. I still have 5 carbons, and if I put in all of my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I still have C5H12. Again, all those lines indicate there will be hydrogens there. So how do I name this one? Well, again, we look for the longest chain, 1, 2, 3, 4, or 1, 2, 3, 4. It doesn't matter which way you look at it. Let's just keep this as our straight chain. So the longest chain I have, this is a butane. And then we have a substituent right here, a methyl group. And we need to tell you where that is. So we're not going to say 1, 2, 3. We want to minimize the numbers and call this 1, 2. 2 methylbutane. Or just straight up methylbutane. Because in this case, it doesn't matter that it's here. The other version of this would be it was here, and that still would be 2-methylbutane. So 2-methylbutane or methylbutane are correct in my mind there. Finally, what's the last one we can actually draw? If I moved this bond here, remember that's actually the same compound. Like I said, it would still just be methylbutane. So I can't move this methyl group here. The only thing that I can do then is think about this group. I can replace this hydrogen with this methyl group. So I can move this bond to the centerpiece. So I can do C2. So I've got my 3 chain in the middle, and now I've got these 2 up top and bottom. That would be the last one. And I can just actually draw this like this. And that would be my last one. Now I can't make any more connections, different types of connections. So what would this one be? Well, the longest chain is just now 3. So this is a propyl, or propane rather. And again, do we really need to count 1, 2? It's the same as counting 1, 2. So it's you don't even have to say 2 here. But at this 2 position, we have 2 methyl groups. So it's a dimethyl propane. You could say 2, 2 dimethyl propane, but you can simplify it and just call it dimethyl propane. All have C5H12, but different compounds. So how would I actually draw these as condensed structural formulas, if that was the question? That's where you would take this, for example, pentane, looking at this one, and you look at each carbon and say that as CH3 right here, CH2, 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 and then CH3. And for, well, this one is not one of ours. So we look at this one over here, it'd be CH3, CH2. Now in this case, you have to actually draw something here. This is CH, but you want to show the branch. So you're going to have to go CH3 and then CH3 on the end. So it's like a condensed structural formula, but with an indication that, yeah, this is branched down there. That's the only way to really draw that correctly. Same thing for this one. If I wanted to, this would be CH3, carbon in the middle. I'd still want to show those branched and then just write CH3. I don't know. I don't like drawing them like this. I'd rather draw them in the structural expanded version like this or the skeletal version. So let's scoot to the next slide to show you the answers here, which we just looked at. Pentane, methylbutane, and dimethylpropane. And how would I draw these the skeletal way? Well, you would start with a carbon and say that's carbon 1, 2, 3, 4, 5. Methylbutane, same thing. We start with a carbon and go carbon 1 to carbon 2. And coming off carbon 2, we've got this methyl group. Then we need this one, 3, 4. Methylbutane, and then dimethylpropane, we would go, well, in this case, 1, 2, 3. So we'll number those 2, 3. And then what's coming off here? Well, again, it's kind of arbitrary how you draw this, but in reality, they'd kind of be off in those directions. Whoops. That would be really the condensed structural formula, just basically that. Or you might see it just drawn like this, as kind of just a cross to show dimethylpropane. All right, a little bit more practice, but now let's bring in the idea of structural isomers, but with alkynes or alkanes. Where can we put double bonds? So it says write condensed structural formulas for all of the alkanes with the molecular formula C4H6, and then name those as well. So give that a second. Pause the video and give that a try. Okay, let's look at this one. So if it's C4H6, well, first of all, like I said, I'm going to start by just drawing out our straight chain of carbons. I know there has to be 4 carbons. I know there also has to be a triple bond. So I'm going to put that right away at the first position to simplify it. So there's my first structure. And that needs an H. This gets no more bonds. It already has 4. And there's our first structure. So what else can we do with this triple bond? I can definitely move it to the middle. But what about moving? Can I move any carbons anywhere to make a new formula? If I try to make a carbon connection here, that doesn't work because this cannot have any more bonds. So I can't really move any carbons around. The only thing I can do with this is move this triple bond, and that would be a brand new structural isomer. So let's try moving it to the middle instead. So there we go. This needs all the H's. Double check that this is 1, 2, 3, 4, 5, 6 hydrogens. This is 1, 2, 3, 4, 5, 6 hydrogens. There we go. Those are different structural isomers, same formula. Can I do anything else? Can I move this here? No, because if I move this here, it'd be equivalent to having it at this position. If I move this here, that's just this molecule flipped over. It's the same molecule. So really, I just have these 2 different types. And how would we name these again? Well, I need to show you where the triple bond is. This is a 4 chain long. So these are both butynes. But crucially different is the position of the double bond. So for this, it's at the 1 position. This one, it's at the 2 position. So just simply 1 butyne and 2 butyne. So there's our structural formulas for alkynes. And here we are. Oh yeah, and I had them drawn out again. This asterisk condensed structural. So you would just convert this into the condensed structural formula like they did here. CH3 carbon triple bonded to a carbon and then a CH3. And similarly with that one. Okay, we mentioned a little bit about cis-trans isomers in our last structure or last video because I mentioned cis versus trans fats. So, or actually, no, I didn't. I apologize. I did not. I mentioned saturated versus unsaturated fats. That's right. I did not mention this. That's okay. So you probably heard of, though, cis or at least trans fats, as there's always a lot of labels saying trans fats are bad, and they are. They're not a natural form of the fats that we find in our oils and butters and things like that. So we create trans fats sometimes through the process of partial hydrogenation. So going from a saturated or unsaturated fat and adding hydrogen across the double bond to turn it into a saturated fat. So that's where this comes into play as well, this world of saturated and unsaturated fats, and we start to create trans fats versus cis fats. So what are these? This is isomers that are specific to double bonds. So let's just flip to this next slide here. If we want an isomer for a double bond, we actually have to have these two switch places. There's not going to be a rotation around this bond because of this pi bond right here. This pi bond does not want to be broken. So if you try to turn this, it's unfavorable. The only way they can actually get a isomer is if these are connected at different points. This is going to be connected in this direction and this direction, and that's going to be the compound. But there is a structural isomer where you have the opposite. The hydrogen is connected here, and the CH3 is connected here. That is not a simple turn of a molecule. That's a brand new molecule now, because you cannot just flip this. So you can have two different molecules with an H on that side and the CH3 on the other side. So this is where we get the cis-trans from. Cis isomer contains alkyl groups on the same side of the double bond, and trans means they're on the opposite side. This helps a lot just to look at this. So here we have two alkenes. Cis 2-butene. That's telling me I have a cis double bond, and there's an ene alkene at the 2 position of this 1, 2, 3, 4 carbon chain molecule. And this says trans 2-butene. Very importantly, remember, this is not a simple rotation. These are not equivalent. If it was an alkane, you can always spin around that single bond. We can't for an alkene. So this is locked into place over here, and this is locked into place over here. Very different compounds. And notice this is cis means the same side. These CH3 groups, the alkyl groups, are on the same side of the double bond. Trans means different sides. So these are on opposite sides of the double bond. So that's how we determine whether something's called cis or trans. So let's take a look at a couple molecules here. Determine whether the following compounds are in the cis or trans configuration. So we're really looking for the alkyl groups and looking for the direction here. So if we look at this one, is this cis or trans? Alkyl groups on opposite sides. So this has to be trans. Notice these are different alkyl groups. That's fine. They're just still alkyl groups though. On this one, looks like we've got alkyl groups on the same side, and we call that a cis double bond. How do we name these? Let's pause here. This is also extra practice. So this is the longest carbon chain here is 1, 2, 3, and 4, and 5. It's kind of drawn a little bit differently than we're used to, but still, this is 1, 2, 3, 4, 5. So this is definitely a pent. And we have a double bond, so it's a pentene. And now we just have to tell you, first of all, what type of double bond it is, cis or trans. In this case, we know it's a trans. And what position is it at? It's not at the 1, 2, 3, 4. It's at the 1, 2 position. We minimize that numbering when we can't. So trans 2 pentene. This one is a different molecule altogether. We have 1, 2, 3, 4, 5, 6 That's a hexene. And we know it's a cis. Now I need to tell you where the double bond is. 1, 2, 3, or 1, 2, 3. Looks like either way, it's cis 3 hexene. So in our bodies, for example, cis versus trans fats, it might seem subtle, but if I look at this, we have these things called fatty acids. This is a carboxylic acid. And they use long carbon chains. Natural fats take this kind of structure. Notice I have an H. Oops. Oh, it's so close. There's an H. Oh boy, I'm ruining this. There's an H coming across there and there. Notice the alkyl groups, big one over here, big one over here, are on the opposite sides right now. Oops, I just threw a trans one. So that's trans versus a cis would look like this. It's harder to draw because the molecules get really big. So now the H is over here, H is over here, and I continue my alkyl chain this direction. Notice how drastically different these look. I'm actually going to change this direction. This looks very flat, or sorry, very linear. The trans configuration is more linear. Notice this big kink. Because of that, H and H on this side, you have to start going the other direction for this chain. So this cis configuration is the natural fats we find from animal fats and the ones our body uses. Trans are not natural. And also notice that they can stack up next to each other in like easier layers than these cis ones. This cis bond makes it harder for these to stack up. And what that means is these can form not precipitate, but these thick sections of fat or these plaques in our system a lot easier than cis ones. And in general, our body just does not like these because they're not used to these. They shouldn't be in our body. They're unnatural. So trans fats are very unhealthy and should be avoided always. That's why all these labels say 0 trans fats. So that's where the cis and trans comes into play with the biochemistry of our bodies. Those were those. Okay, we are almost done. We are on to the last section here, optical isomers. These are interesting because these are probably the toughest ones to think about, I think. But isomers that have the same structure, like our hands, look at your hands right now, and notice they look very similar to each other, but have your left palm facing up and your right palm facing down. They look like they match up, but now flip them both palm up and stack them on top of each other. Notice they don't look the same. You can't match them up perfectly in that same direction. That's because they're not superimposable. They're mirror images, but they're non-superimposable. And this is something that we call chiral. They're chiral things. They're chiral pairs. So molecules can have a chiral pair. If you have a molecule CHBrCl, 4 different things, and I draw that same molecule like this, say it's looking at itself in a mirror, it becomes ICLHBr. Right away, they might look like the same molecule, but this is just like your hand. If I turn this on and try to flip it on top of this one, I can't get them to match up. So they're very similar, but subtly, at this center, there's a subtle connection difference, and it comes from connection, directionality, and where they're connected. So those are chiral molecules. These chiral centers, as we call them, they only happen when you have 1, 2, 3, 4 different things connected. You have to have 4 different things connected to a carbon center for them to produce this concept of chirality. So these two would be optical isomers of each other. Hard to see on paper. This really helps to get a model and look at it in class. And after this lecture, I'm going to try to find some interactive 3D thing online for you guys to look at as well. So again, yeah, here's the mirror version of this. And here is kind of what I did. You have this A, B, C, D, 4 different things. And this brand new molecule over here is its mirror, non-superimposable mirror image. This is what I just mentioned. It says two tetrahedral complexes that contain the same set of 4 unique groups. We would call those optical isomers. So it has to have 4 unique groups on the carbon center. Kind of interestingly, how we figure this out experimentally, light actually is his own kind of directionality. So we can actually take a specific polarity of light and shine it at those molecules, and it actually kind of rotates the light in a specific direction. So different enantiomers, different optical isomers, if I have light coming in here, it might rotate the light like this. If I light shining at this one, it might rotate the light like that. And you can actually detect that using instruments. So we can actually tell the chirality of molecules, a solution of them, using these kind of techniques. Again, this is just a very brief introduction of all this stuff. You'll get a lot more of this in organic chemistry. So how do we actually analyze for some of this stuff? This can be tricky, especially on flat pages, I'll be honest. So this question says, determine whether the following kinds of molecules are structural isomers, cis-trans, or the same molecule. So, and then it says, if they appear to be the same molecule, can they exist as optical isomers? So that's a good question. So let's first look at this first one. First of all, in terms of connections, these all have the same exact connections in terms of bonds. So to me, this is looking like the same exact molecule. Notice you might look like they have different connection points, but if I think of this as, I'm going to redraw this, carbon, Cl, Cl, using my 3-dimensionality a little bit. So notice now I'm looking at it where this is coming out of the plane, this is going behind the plane, and these are flat in the plane. This molecule right here, we can think of it as looking at it from this direction. If I look at it from that direction, that's the same kind of molecule. This is kind of looking at it from the top, but notice it's the same thing. These chlorines are both on that plane over here. Whoops, come back. Notice they're right here, and these H's are in the same plane over here. This is the same molecule. It really is. And also, can it be optical isomers? No, because not 4 unique groups. These would have to have 4 unique groups connected to that carbon. This is why doing this on paper is pretty tricky sometimes. You have this model in front of you, you can tell this is the same compound as that, exact same. What about this one? Well, right away we see there's a double bond involved. So I would, is this a cis-trans situation? Notice that this isn't not an alkyl group, but it doesn't need to be an alkyl group. It can be anything, any other group other than H. So these are bromo groups, and notice the only difference here is that they're on different sides of the double bond. So this would be a different sides trans, and this is cis. So these are cis-trans isomers. Finally, this versus this. Again, I'm going to start looking at connection points. This carbon here is connected to a chlorine, CH3, and an ethyl group. This carbon here is same, and they're also connected to this 3-carbon chain. So I'm leaning towards same molecule again. It's possible that they could be optical isomers, but if you look at this and try to think, what if I just flipped this direction? What would this look like? I'm going to just flip it around like that. It would be chlorine going to it was going to the left, so now it'll be going to the right. This should be on the bottom, and this should be on the top. Okay, now let's compare this to this. I physically just flipped this same molecule upside down. Yep, that's connected the same. The only difference is this and this connection. But remember, this thing can spin around as much as it wants, and I can get from here to here. So these are the same compound. Again, this is not easy to see. It's not really easy to tell that these are the same compound. If you had a model kit, you could really tell that these are the same compound. If you do have a model kit at home, build just this section of it and compare the two. See if you can turn this bond right here so that it matches up with this, or this over here. You should find that to be true. It's just tough to see on paper, and this is a really tough thing for me to try to teach via just this PowerPoint kind of method here. So take some practice, look at more of these problems, go online, find some models, and that'll help you kind of identify these better. This will probably be one of the most tricky things to do on paper in this section, is to try to predict whether these are the same molecule or not, or structural isomers or optical isomers, etc. So, but for now, that's where we're going to end. Here are the answers that I just went through. You can take a look at the review sections here and read through the chapter. There's a lot more examples in there. And I will see you guys in the next section.